There is a discussion going on the chat.
I just tried to answer the question about PP scattering.
Yeah.
If you stipulated unlimited computing power, there'd be no trouble to calculate PP scattering with a classical computer. More realistically, you might need a quantum computer because of the real-time nature of the process.
We are about to start again.
So shall I share my screen then?
Yes,
Yeah.
Enrico,
Yes. Okay, so
we'll share the session.
yeah, let's start the second part.
Okay.
And our next speaker is the Charles Simoni Professor at the Institute for Advanced Study, Edward Witten. So you can start, and you have 40 minutes plus 10 for questions. Thank you.
Thanks very much for the invitation, and thanks as well to the organizers for putting this session together and for inviting me to speak. I've certainly enjoyed the first two talks. So the title that was suggested was about Weinberg and the role and meaning of symmetries in physics. I've slightly altered the title. And so this topic is extremely broad, as there were so many facets to Steve Weinberg's contributions to understanding the role of symmetries in physics. So I tried to make a list of highlights, most of which we've heard at least a little bit about from the first two talks. There was his early interest in spontaneously broken global symmetry, with several proofs of Goldstone's theorem, or as they called it, Goldstone's conjecture with Goldstone and Salam. There were low energy theorems for soft gravitons and photons, and the relation of these to gauge invariance and general, the relation between assuming that a photon or graviton doesn't decouple at low momentum and a requirement of gauge invariance or general covariance in its couplings. Then there was current algebra and effective field theory, spontaneously broken symmetry in the hadronic world, spontaneously broken gauge symmetry and the standard model, approximate global symmetry as an accidental consequence of gauge symmetry, and effective field theory as the central truth of modern physics. So, well, those are at least 6 main topics in Steve's work on the significance and role of symmetries in physics. And we didn't hear much about the second one in the first two talks, but the first two speakers said a fair amount about most of the other 5 topics here. So my own most vivid personal recollections of Weinberg have to do with learning about current algebra and effective field theory from Weinberg. So I came to Harvard as a postdoc in the fall of 1976. So Weinberg had called me up to make the offer. I accepted on the phone, which seemed to surprise him slightly. When I was at Harvard, we used to have weekly family meetings. And so somebody would make a presentation about something of current interest. But if something came up in those discussions that Weinberg thought other people didn't understand, he'd make a little lecture about his understanding of it. And current algebra was clearly a subject which he was dissatisfied with how well people understood it, because he would regularly give a short lecture on his understanding of current algebra. I was one of the physicists who didn't understand current algebra when I came to Harvard. I'd been exposed to the traditional way that self-plan theorems were deduced by manipulating currents and various clever arguments, but it seemed like hocus pocus. So I was one of the targets for Weinberg's lectures in current algebra, and the way I personally learned about soft plans and effective field theory and hadronic physics was from the lectures he used the informal talks he would give at his the family meetings whenever current algebra came up. Now, I spent part of the weekend rereading some of Steve's most classic papers on the role and meaning of symmetries, trying to think about the best way to approach this lecture. And well, it's a strange experience because often your reaction when you read something is, but everyone knows that. Then you have to pinch yourself and realize that this paper is why everyone knows that, or where everyone knows it from. So one option for the talk was to organize it around highlights of some of the classic papers. But many of them are well known, and I suspected some of the most important would figure in other lectures this afternoon, or morning if you're in the East Coast of the US. So I decided it would be more fun to organize the talk around some of the lectures and articles in which Steve explained the evolution of his own thinking about physics. And I picked three that were spread out in time. So first was the Nobel Prize acceptance speech in 1979. Then an article almost 2 decades later, what is quantum field theory and what did we think it is? And then after another 2 decades, half a century of the Standard Model. So we'll look at those three talks and how he explains how his thinking evolved up till that point. And we'll see that there's a sharp change between his outlook in the first one and in the last two, which is in a sense, a more modest view of what we understand and a description of everything in terms of effective field theory. A main theme in the last two is that whatever we've done should be understood as an effective field theory. So that was kind of explained in Howard's lecture. So the first of the three of Steve's lectures and articles that we'll look at closely is the Nobel Prize acceptance speech from 1979. So a main theme of this lecture is that there were two central organizing principles, as Steve sees it, in the development of the Standard Model, which were symmetries and normalizability. So he writes, to a remarkable degree, our present theories of elementary particle interactions can be understood deductively as a consequence of symmetry principles and a principle of normalizability that's invoked to deal with the infinities. After 1905, with special relativity as a precedent, physicists viewed symmetries as practically sacred. Symmetry principles took on a character of universal principles, expressions of the simplicity of nature at the deepest level. So Steve explains that then it was very difficult to become accustomed to imperfect and partial symmetries. So isospin is an imperfect and partial symmetry. It's not a perfect symmetry. It's really only a symmetry of strong interactions. And later there were other imperfect and partial symmetries like strangeness. So Steve says it was painfully difficult to become accustomed to imperfect and partial symmetries. And later there were shocks of learning that some of the supposedly perfect symmetries were actually imperfect. P and CP were both violated. So nature was not as perfect as assumed. Well, why was it so hard to accept the idea of symmetries that are only approximate or only apply to some interactions? Steve writes, if symmetry principles are an expression of the simplicity of nature at the deepest level, how can there be such a thing as an approximate symmetry? Is nature only approximately simple? Well, a turning point, so this is the background to the impact on him of the idea of spontaneously broken global symmetry, which he learned about from the work of Goldstone and others, such as Nambu. After learning of the idea of spontaneous breaking of symmetry, Steve writes, as theorists sometimes do, I fell in love with this idea, but as often happens with love affairs, at first I was rather confused about the implications. So first of all, why was Steve so excited about spontaneous symmetry breaking? Well, he was troubled, as he writes, about the approximate and imperfect symmetries, and he hoped to promote the approximate and imperfect symmetries to exact a priori symmetry principles, where the imperfections were brought about by spontaneous symmetry breaking. It was therefore rather disturbing to hear of a result of Goldstone showing that exact spontaneously broken continuous symmetry implies the existence of a Goldstone boson. So Steve became extremely interested in this result, and one of his important early papers that you've heard about already in this session with Goldstone and Salam consisted of 3 proofs of Goldstone's theorem. We call it Goldstone's theorem, but they describe it as Goldstone's conjecture, for which they gave 3 proofs. At the time, Weinberg's conclusion was that spontaneous symmetry breaking is not a useful idea for fundamental physics, because in nature there weren't any Goldstone bosons. Goldstone bosons, at least in the strong interactions, would already have been discovered. And he explains that he tried to add a epilogue to their article, which would have quoted Shakespeare expressing a lament that spontaneous symmetry breaking is a useless thought, but the editors censored it. The editors of Physical Review didn't allow that to go into print. Now, Peter Higgs and others showed by about 1964, following ideas that came from condensed matter through Phil Anderson, and also ultimately going back to Julian Schwinger's paper on the Schwinger model, they showed that spontaneously broken continuous gauge symmetry does not lead to existence of a Goldstone particle. Here, the emphasis is on the word gauge. So Goldstone's theorem was for spontaneously broken global symmetry. Higgs and others showed that for spontaneously broken gauge symmetry, there's no Goldstone particle. But Weinberg writes, physicists who heard about this, but I've added the word particle because, of course, it wasn't regarded as a technicality by people who knew about superconductivity. But anyway, particle physicists who heard about this generally regarded it as a technicality. And it may have not attracted so much attention because of a new development, the Adler-Weisberger sum rule, which in Weinberg's telling turned Goldstone bosons from unwanted intruders to welcome friends. So the idea of the pion as Goldstone boson of a spontaneously broken approximate chiral symmetry is earlier. It goes back to work of Nambu and others around 1960. But it was the Adler-Weisberger, I left out the ER, sum rule that got Steve really excited about current algebra. I often heard him, both at those family meetings I mentioned before and later, say that this sum rule got quantum field theory back on track after years in the doldrums. So the original formulation was different, but Steve reinterpreted the Adler-Weisberger sum rule as a current algebra formula for low-energy pi nucleon scattering, combined with a more general dispersion relation that was already previously known. And as you've already heard from the last talk by Howard, he spent much of the years, starting in '65, working on current algebra and reformulating it in terms of effective field theory. He introduced effective field theory as a tool that makes it straightforward to calculate the consequences of spontaneously broken exact or approximate global symmetry. That was enormously influential at multiple levels. First, it made current algebra transparent, and it was a prototype for thinking about other aspects of physics. As I'll explain later, Steve came to view it as the central organizing principle of our understanding of physics, effective field theory. But just for current algebra, I don't even know if young physicists today learn how current algebra was done before effective field theory was introduced as a tool. There were clever arguments about endpoint functions of currents, low energy behavior of amplitudes, and a little bit of hocus pocus. So the current algebra approach was so much more transparent and simple to use and to generalize to higher orders that the older approaches really went into eclipse. So as I said, I as a graduate student learned the older approaches, but I don't know if at what point younger physicists, or until when younger physicists have done so. The other strain of thinking that went into the standard model was renormalizability. So as Steve tells, a lot of physicists had viewed renormalization of divergences as sweeping problems under a rug. But Weinberg's view was different. Here's what he writes in his Nobel Prize acceptance speech. I learned about renormalization theory as a graduate student, mostly by reading Dyson's papers. From the beginning, it seemed to me to be a wonderful thing that very few quantum field theories are renormalizable. Limitations of this sort are, after all, what we want, not mathematical methods which can make sense of an infinite number of physically irrelevant theories. I thought renormalizability might be the key criterion, which also in a more general context would impose a precise kind of simplicity on our theories and help us pick out the one true physical theory out of the infinite variety of conceivable quantum field theories. Well, soon after getting his PhD, Weinberg proved a relatively difficult theorem, Weinberg's theorem, probably his most significant result before the paper with Goldstone and Salam, although perhaps I'm overlooking something, that in a sense completed the proof of renormalization theory. He proved something that the founders had probably in generality assumed, which was that if you have a Feynman diagram, which overall is convergent by power counting, and all its subdiagrams are also convergent by power counting, then the diagram is actually convergent. Well, jumping back to 1967, jumping ahead to 67, by 67, Weinberg was trying to make a gauge theory of the strong interactions. He wanted to turn chiral symmetry into a spontaneously broken gauge symmetry with the rho and A1 as gauge bosons. Well, one thing you'd worry about that is that, or at least one thing that comes to my mind right away, is that the rho is relatively conspicuous in hadron phenomenology, but the A1 isn't. It exists, it's relatively heavy. If you want SU2 times SU2 chiral gauge bosons, the rho isn't enough, so you need the A1, but that's a little worrisome. But worse than that, the pion was also supposed to be a pseudo-Goldstone, an approximate Goldstone boson of the same symmetry. With our modern understanding, that's clearly wrong. You can't make the same symmetry, both a gauge symmetry and a global symmetry that would have Goldstone bosons. So it won't come as a surprise that the pieces didn't fit together. But at some point in the fall of 1967, I think while driving to my office at MIT, it occurred to me that I'd been applying the right idea to the wrong problem. It's not the rho that's massless, it's the photon. Its partner is not the A1, but the massive intermediate bosons, which since the time of Yukawa had been suspected to be the mediators of the weak interactions. Once the ideas were in place, Weinberg writes it was not difficult to make a model. And soon what we now call the Weinberg's law model of electroweak interactions was born. Riccardo showed the Lagrangian in his talk. But Weinberg didn't make much progress in proving renormalizability. And he writes that was partly because he tried to use unitary gauge, which is notoriously difficult to understand, but also he was hampered because of lack of familiarity with path integrals. Weinberg says he was initially skeptical of the work of Hooft and Veltman because of unfamiliarity with path integrals. In fact, in one of the later lectures, he explains that in this period of his career, he viewed path integrals as a throwback to an earlier epoch in which physicists distinguished particles from fields. Whereas, in his view, in today's view, but also in Weinberg's view at this time, the correct picture is that everything are fields. Particles arise from quantization of fields. And path integrals, for example, in the Feynman and Higgs book, he points out, are expressed in particle language, not a field language. And so Weinberg was initially skeptical because of not familiarity with path integrals applied to field theories in particular. And he writes that it was the work of Ben Lee, who derived de Hooft's Feynman rules from canonical quantizations, that resolved his skepticism and convinced him that what we now call spontaneously broken gauge symmetry is renormalizable. Assessing the electroweak theory in his Nobel Prize speech, Weinberg says it's all very nice that the original model has passed experimental tests, but he would not have been too disturbed if it had turned out that the correct theory was a different one based on the same ideas. The important thing was a spontaneously broken was an exact but spontaneously broken gauge symmetry. He then goes on in the lecture to talk about the strong interactions in QCD. So experiments increasingly have confirmed QCD as the correct theory of strong interactions. Although the experimental tests, although they were impressive by 1979, when he gave this lecture, of course, are nothing compared to what we have today. But then he highlights one consequence, which also was discussed in some detail by Howard. It's the impact of QCD on our understanding of symmetry principles. The constraints of gauge invariance and normalizability proved enormously powerful and forced the Lagrangian to be so simple that the strong interactions, as described by QCD, have to conserve a lot of global symmetries that are not exact symmetries of nature. Here's some of them. I guess we should also add strangeness and flavor SU3 and parity. Famously, this doesn't work for CP. Not parity, therefore. Famously, it doesn't work for P or CP, which led to Steve's proposal of the axion to fix that issue. And that, of course, is a still unresolved question in physics, whether there really is an axion, whether that's the right interpretation of why the strong interactions conserve CP. Concluding the lecture, he writes, I suppose I tend to be optimistic about the future of physics, and nothing makes me more optimistic than the discovery of broken symmetries. So that's Steve at the Nobel Prize acceptance in 1979. Now we're going to jump ahead almost 2 decades to what is quantum field theory and what did we think it is. And as you see, the main change is a rethinking of everything, reformulation in terms of effective field theory as the central tool to organize what we know. So here's Weinberg describing his views early in his career. And it'll be, of course, the views that he described in the Nobel Prize speech. Well, first of all, 2 things especially attracted me to normalizability in field theory. One was that the requirement of normalizability is a precise and practical criterion of simplicity. And the other thing, I think this one is interesting, and this one he doesn't really critically discuss later, at least in this lecture, to what extent it held up or doesn't hold up. The other thing I liked about quantum field theory was it gives a clear answer to the ancient question of what it means for a particle to be elementary. It's just a particle whose field appears in the Lagrangian. So with the modern duality understanding, well, one of the limitations of this statement, which Steve really doesn't discuss in the lecture, has to do with dualities. So anyway, Steve explains, as Howard also did, that he changed his viewpoint largely in the course of teaching about quantum field theory at Texas and writing his books. He came to view quantum field theory as the inevitable low energy outcome of relativity plus quantum mechanics plus cluster decomposition. So quantum mechanics means that you're going to have a Hamiltonian, a Hilbert space and a Hamiltonian acting on it. But relativity, well, okay, why is the Hamiltonian built as an integral of local operators? Because there has to be another Hamiltonian in a different Lorentz frame. And if you want to have Hamiltonians in different Lorentz frames, or if you want Hamiltonian quantum mechanics to be relativistic and satisfy cluster decomposition, he claims to show that the Hamiltonian has to be the integral of local operators. So you get the structure of quantum field theory. Why are there Lagrangians? Because otherwise there's no link between symmetries and conservation laws, and Lorentz invariance is difficult to achieve. So he writes, he says, although you can't argue, I think he means you can't argue rigorously that relativity plus quantum mechanics plus cluster decomposition leads only to quantum field theory. He said you can't argue this because he points out string theory as an example of a theory that satisfies relativity, quantum mechanics, and cluster decomposition, but it's presumably not a quantum field theory. So you cannot argue that these principles lead only to quantum field theory, but you can argue, it's very likely, that at sufficiently long distances, any such theory looks Lorentz invariant and satisfies the cluster, you can argue that any theory that at sufficiently long distances is Lorentz invariant and cluster decomposed will also look like a quantum field theory. So he's saying that you can't argue that these principles lead only to quantum field theory, but that anything that satisfies them will look like a quantum field theory at low energies. I think most physicists today would find this convincing, and certainly I do. Although a quibble is that, a quibble is that his derivation does not apply to theories that aren't infrared free, and so cannot be described in the language of particles. But his statement is also believed to be correct in that case, even though his explanation does not apply to that case. So anyway, this is Steve's explanation of why quantum field theory, that it's the inevitable low energy consequence of more general principles, which he takes to be relativity, quantum mechanics, and cluster decomposition. Cluster decomposition just means that a process here can be described independent of a process in the next galaxy. Well, what's the reason for the gauge invariance of the standard model and general relativity? One possible answer is that it's the only way for massless particles of spin 1 or 2 to have non-trivial couplings at low energies. This is a reference to the work he had done in 64 and 65 on soft theorems and QED and gravity. And in my list of 6 topics at the beginning, it's the only one that the previous 2 lectures didn't really say much about. And I won't either, because I want to go into other things. But I would quibble slightly with this proposed explanation. I would say that this is a true and important fact, that the only way for massless particles of high spin to have non-trivial low energy couplings is to have gauge invariance and general relativity. It's a true and important fact. It's one of the many things that Steve pioneered back around 1964. And his work on these questions was the state of the art until the last few years. But I don't find it convincing as an explanation. To me, it shifts the question to why there are massless particles of spin 1 and 2 that do not decouple at low energies. And I don't think we have better explanations today. I don't think we have a full understanding today. Now, as I've already foretold, in 1997, relative to his earlier view, Weinberg drastically demoted the concept of renormalizability. He no longer saw it as a fundamental principle, but rather as a powerful tool in looking for a useful description of most of the experiments we can actually do, because we're mostly limited to comparatively low energies. In other words, quantum field theory, for instance, to begin with, is not necessarily fundamental. It's the inevitable outcome of more general principles. But a refinement of this statement is that quantum field theory at sufficiently low energies always looks renormalizable. And so that was, by 1997, Weinberg's view of why renormalizable is useful. Most of the experiments we can do are going to be describable by a renormalizable quantum field theory, because first of all, quantum field theory is inevitable at sufficiently low energies, but at energies well below the cutoff, whatever it is, any quantum field theory will look renormalizable. So that's in spirit a Wilsonian view, as Howard also remarked. So Weinberg emphasized that all our theories of today are effective field theories, low energy approximations to something that's potentially much different at short distances. So he writes, the present educated view of the standard model and general relativity is that these are the leading terms in effective field theory. I don't see why anyone today would take seriously Einstein's theory of general relativity if by Einstein's theory is meant the theory with the Lagrangian just given by the usual Einstein-Hilbert term. So the theory should be the Einstein-Hilbert term plus higher order corrections. And actually, at just approximately this time, one also learned that there's a lower order correction, the cosmological constant, that also needs to be added. Likewise, he writes, since we know that without additional fields, there's no way that the renormalizable terms in the standard model could violate baryon conservation or lepton conservation, we now understand in a rational way why baryon and lepton number are as well conserved as they are, without having to assume they're exactly conserved. Unless someone has some a priori reason for exact baryon and lepton conservation that I haven't heard, I'd bet very strong odds that baryon number and lepton number conservation are in fact violated by suppressed non-renormalizable corrections to the standard model. This lecture was published in 1997, so it's pretty close to the time when experiment was making this statement clear in the case of lepton number conservation. It's unfortunately still not clear today for baryon number conservation. So Steve goes on to address the relation of quantum field theory to S-matrix theory. So quantum field theory had had difficulty in the late 50s and early 60s. Some physicists had said, well, maybe field theory is wrong and the fundamental principle is just relativistic S-matrix theory. Steve had always viewed it, S-matrix theory as impractical. So even though he was at Berkeley, the epicenter of S-matrix theory during some of the crucial years, he had never found it appealing. But he says that quantum field theory is S-matrix theory made practical, by which he means the following. So specific quantum field theories like the standard model make detailed predictions. But he writes, the general structure of quantum field theory has no content beyond the general principles that went into S-matrix theory. Because if you allow yourself arbitrary terms in a low energy expansion of an effective field theory, you end up generating in a low energy expansion the most general S-matrix that's consistent with general principles. Interestingly, though, Steve remarks that he considers the emphasis on analyticity in S-matrix theory to have been misguided, since he views analyticity as a consequence of the more basic principles, relativity, quantum mechanics, and cluster decomposition. Weinberg actually proved a theorem with Joachim Gomez that they describe as proving that order by order in perturbation theory, an arbitrary theory can be renormalized, provided one's willing to include all possible local operators as adjustable counterterms. I think you could describe it by saying that including non-normalizable operators does not lead to any anomalies beyond the known ones that occur for minimally coupled fermions, or at least this assertion is part of the theorem. So, in the concluding part of his talk, Weinberg responds to those who found it discouraging to demote the gauge invariance and other aspects of the standard model from fundamental principles to low energy approximations in an effective field theory. So he's responding to those who find it discouraging to question the fundamental significance of the deepest theories we have. He says, in regarding the standard model and general relativity as effective field theories, we're simply balancing our checkbook, realizing we perhaps didn't know as much as we thought we did. But this is the way the world is, and now we're going to take the next step and find an ultraviolet fixed point, or much more likely, find entirely new physics. So that's the note on which he concludes in 1997. So we'll jump ahead to 2018, near the culmination of Steve's career, where he looks back on half a century of the standard model. So here's Steve's assessment of where physics was when he started. Feynman, Schwinger, Dyson, and Tominaga in the late 40s had figured out how to calculate in QED in a Lorentz invariant way and to deal with the infinities. But more than that, the theorists of the 1940s had discovered a rationale for the simplest version of quantum electrodynamics. The symmetries of electrodynamics, Lorentz and gauge invariance, by themselves would not take you very far. For instance, you could add terms to the Lagrangian that would make the magnetic moment of the electron anything you like. But then renormalization would not work. For the theory to be renormalizable, the Lagrangian had to be very simple. And it was in just that simple theory that you could calculate specific results and get stunning agreement with observation. So for instance, you got a unique answer for the magnetic moment of the electron if you make the theory renormalizable. If you don't, you have a more complicated theory, it's not renormalizable, and there's no predictive power for the magnetic moments. So that's what had attracted Steve to QFT. In the 1950s and much of the 60s, it was hard to make progress with quantum field theory. So some physicists, not Steve, explored S-matrix theory, trying to understand the S-matrix by general principles without field theory. This aim, he writes, was in a sense achieved much later in effective field theories, but it could never be implemented in the way that was tried in the 1950s. Complex analysis with many complex variables is just too hard. When he says the aim was achieved in effective field theories, he means what I said before, and I think we'll repeat it in a different way, that if in an effective field theory, you allow in a low energy expansion arbitrary local gauge invariant terms that satisfy any fundamental symmetries you want to impose, then at least in an expansion in the energy, you generate the most general S matrix consistent with all the principles you've imposed. So anyway, this is what attracted Steve to quantum field theory, and this is what didn't attract him to S matrix theory as a substitute for quantum field theory. Now Steve writes, the importance of symmetries was clear, but there was a puzzle. Why were there approximate symmetries? so roughly as he had said in the Nobel Prize speech, he writes, if symmetry principles are fundamental truths about nature, how could they be approximate or apply to some interaction, not others? If they are not fundamental truths, what are they? And as in his Nobel Prize acceptance speech, he went on to tell the story of how the standard model had developed. I won't repeat that part of it. So now we have the standard model, he writes. He says, I guess, since this was originally a lecture. Its success is also the success of quantum field theory. Or is it? Since the 1970s, we've understood that within broad limits, any relativistic quantum field theory will look like a quantum field theory, what's called an effective field theory, at energies E less than some fundamental scale M. As I like to put it, non-renormalizable theories are just as renormalizable theories. This is what he'd proved one version of in the paper with Gomez that I mentioned before. He means by this that an arbitrary theory free of the usual anomalies can be renormalized order by order in perturbation theory, provided one's willing to allow all possible counterterms. But to a certain order in the energy, only finitely many counterterms are important. So you gotta, if M is the cutoff, then to a given order in 1 over M, you can describe all observables in terms of finitely many adjustable parameters. But if you manage to measure to a higher order in 1 over M, you'll encounter more adjustable constants. So to me, this discussion by Weinberg raises a question about which, as far as I know, he never directly expressed an opinion. He's saying that order by order in perturbation theory, you can construct a family of unitary physically sensible S matrices with the coefficients of all possible local operators as free parameters. To me, this raises the question, do unitary S matrices with those parameters actually exist, or is this only a perturbative statement? I actually wonder if Steve, to my knowledge, he never addressed that question. I never heard it, and I didn't see it in any of the papers. I actually wonder if he considered the question irrelevant because of his view that quantum field theory was fundamentally effective field theory. But he didn't explicitly say that he considered it irrelevant either, as far as I can see. So I'm not sure. He also, at times in his career, was very interested in ultraviolet safety, the existence of a UV fixed point, possibly including gravity. And as he would usually say when he discussed ultraviolet safety, that would be a framework that would very likely allow only a finite number of free parameters corresponding to relevant or marginal perturbations. So if ultraviolet safety is correct, that would be a principle that would select a very small family of the infinite dimensional family, and maybe those are the theories that really exist non-perturbatively. Steve had a consistent interest in this idea, which might entail a fundamental quantum field theory that really exists non-perturbatively. But as far as I know, when he generally viewed this as a sort of dark horse, not the most likely prospect. He used to say, and that includes in the lectures I'm describing, that the likeliest future prospect would involve a completely different kind of physics, possibly string theory. But Steve always used to try to be open to all possibilities, including the ones that look less likely. So he would often discuss ultraviolet safety as an option. But anyway, regardless of whether you think ultraviolet safety is the way to go, the question of whether the family of unitary relativistic S matrices, depending on infinitely many parameters, really exists, or only makes sense in perturbation theory, as I said, I'm not aware that Steve ever expressed an opinion. For what it's worth, I think it's an interesting question, and I'm not sure of the answer, but I tend to think the answer is no. If the answer is yes, I don't think it will be because there is a universal fixed point that has all the infinitely many parameters as relevant operators. I think it's more likely that the generic theory has a UV limit of a type unfamiliar to us, not the ordinary local quantum field theory fixed point. So I guess the answer is no, but if it's yes, I think there's something in the ultraviolet that we really don't understand. That's the ultraviolet of a generic theory in this family. So I think that for the same reason Steve said that asymptotic safety would leave only finitely many parameters. Anyway, Steve in 2018 considered any quantum field theory to be as good as a renormalizable one. What's special about quantum renormalizable theories, he explains, and I've said this already, is that any theory looks renormalizable, possibly free, which is a special case of renormalizable. But anyway, any theory looks renormalizable at low energies. Unfortunately, in most observations, only relatively low energies are accessible to us. Famously, the existence of gravity is one probe of high energies. Neutrino masses are probably another, though we don't know for sure. In inflation and cosmology, we probably are getting a window beyond renormalizable energies. And baryon non-conservation might ultimately be another window. There can be a few, but mostly we only are able to probe relatively low energies. And Steve writes that with hindsight, that's why the search for renormalizable theories turned out to be such a good idea. Remember, in the early part of his career, symmetries, including approximate symmetries, and the drive for renormalizability was the driving force. And with hindsight, he's reinterpreting why it was a good idea, but it was a good idea because whatever was the truth of nature at accessible energies, it was likely to be ascribable by a renormalizable theory. Now, as in the previous two lectures I summarized, as well as some others that were described by Howard, Weinberg notes that global symmetries can be low energy accidents resulting from the structure of gauge couplings, and as such are likely to be violated by corrections to the renormalizable part of the standard model. By 2018, he could point to neutrino masses as a likely confirmation of this picture. Unfortunately, only a likely confirmation because there are other conceivable models, interpretations of neutrino masses. And I think I'll leave the last word to Steve. Steve was often finished his lectures on an optimistic note, and here's what he said at the end of this one. The present generation of young physicists may envy those of us who had the excitement and delight of developing the standard model. This might be a mistake, just as it turned out that my generation would have been mistaken to have envied the earlier heroes of quantum electrodynamics. Our newly minted experimentalists and theorists now have a chance to participate in taking the next big step beyond the standard model. They may even be able to see their way clear to the very high energy scale where a final theory will be revealed. Thank you for your attention.
Thank you very much for this very interesting talk. So I think we have time for a few questions. Let's see. Alberto.
Hi,
Yeah.
can you hear me?
Yes.
Hi. So I would like to understand better your point about massless spin 1 and spin 2
Yes.
particles. Somehow you're saying there could be particles like that that completely decouple at low energy, so somehow they don't have any
It depends.
monopoly interaction, they can only interact with mu, for instance.
Well, it's more clear in the case of spin 1. So in conventional quantum field theory, you could certainly have a U1 gauge field with no charged particles that it couples to. So it would couple only through F mu nu, and therefore it would only have derivative couplings.
That's true. Still, we would need, if we were to write Lagrangian, a local Lagrangian for it, we would need an A mu with the local gauging.
That's true. Although you couldn't deduce it the way Steve approached it. You're right. That's right. Yes. That's a valid point. So at least in Lagrangian field theory, Steve's argument assumed non-decoupling, but you could make another argument if you assume Lagrangian field theory. Steve's argument was sort of S matrix theory plus non-decoupling, and then he tried to deduce properties of Lagrangian field theory. But you're correct, I think, that in Lagrangian field theory, to write a local Lagrangian for the massless spin 1 field, I think requires gauge invariance because it doesn't have enough felicity states to be described otherwise.
Thank you.
But let's go back to what Steve said, though. See, okay, what you said is valid. I think perhaps possibly as an objection to what I said, but I will stick with what I said as a possible objection to what Steve said. So he proposed that the soft theorem was an explanation of the general covariance in the real world. But it's only an explanation of general covariance if you know about the existence of a massless spin 2 particle, which most people would say is part of what you're trying to explain. Anyway, unfortunately, okay, because there were so many other things to discuss, I didn't explain in much detail Steve's work on the soft theorems in 64 and 65. It was certainly one of his important contributions, and he made important discoveries about that circle of ideas. I'm just quibbling with exactly what you learned about the relations between the different ideas. But there's no question those were important things. I see a question from, well, I see several hands up.
Yes, there are several. Maybe let's see if we, first was Georgi.
Hi, Edward. That was a very nice talk, very insightful. I have a question about the part where you mentioned string theory as a possible sort of new physics that is consistent with effective field theory. Do you see ways of string theory going beyond effective field theory, and could you comment on that in what way that could happen?
Well, effective field theory is valid at low energies and long distances. So as far as we know, there's no way to get around effective field theory at low energies and long distances. If there was, it would be incredibly important, regardless of whether it came from string theory or someplace else. I mean, I've thought a lot, but fruitlessly, and I'm sure others have, of whether there's any way consistent with general physical principles that you could modify effective field theory at long distances. As far as I know, the answer is no. I'm never going to claim something like that as an absolutely bulletproof statement. Maybe someone will show that, who knows how.
How about examples in string theory of backgrounds where the short distance and the long distance mix, the so-called UVIR mixing? Can you comment on that?
I believe you can always describe it as I believe the mixing description, it's too complicated and technical to remember all the answers, but I believe actually you can't really violate effective field theory in a situation where an effective field theorist would expect it to be valid.
Even in time-dependent backgrounds?
I can make no promises. Time-dependent backgrounds aren't that well understood in string theory. And it's conceivable, it's definitely conceivable there are surprises there. I mentioned that Steve never expressed an opinion on whether the infinite family of theories exists non-perturbatively. And I also said I thought it was an important question, but I didn't quite explain why. In the 1 + 1 dimensional case, if that infinite family of theories really exists non-perturbatively, it would be the natural arena for string field theory. I tend to believe it doesn't, but I don't know that. If it does, the UV is not something standard like a fixed point. It might be something more like the TT bar deformation of Zamolchikov.
Okay, thank you.
Maybe we have time for one last question. Alexander.
Myself.
Okay.
Cannot unmute myself. Now, okay, thank you. Yeah, thank you for this very nice reconnection, this talk, very nice. So I have one question. I mean, the argument of deriving QFT at low energies and also string theory, it's cluster decomposition, relativity, and quantum mechanics, as you say. Is there any way of parameterizing what happens if you were to give up the canonical way of standard quantum mechanics, so to speak, in this argument? Is there a way of parameterizing what would come out of this?
You want to give up, you want to modify quantum mechanics?
Yeah, something in some way, in some controlled way, so and then see what comes out at low energies, whether there's something else than these two known consequences.
I have bad news, which is even if you don't have relativity and cluster decomposition, well, I think you might, sorry, even if you don't have relativity, just from, there's no known way to modify quantum mechanics, keeping cluster decomposition and being physically sensible. So let me give you an example of that statement. Mm-hmm. So Google did this famous experiment where they had 57 qubits and they did a complicated calculation. and got answers that went beyond what you could check with a classical computer, or at least that's their original claim. And they definitely tested quantum mechanics under conditions of complexity much greater than those where quantum mechanics had ever been tested. But they did not describe their experiment as a test of quantum mechanics, even though it clearly was a very interesting and new test of quantum mechanics under conditions quite different from any previous test. Why did they not say it was a new test of quantum mechanics? They actually did not say why they didn't, so I'm only guessing. But I believe the reason they didn't is that there's nothing to compare quantum mechanics to. Because there's no physically sensible candidate theory that modifies quantum mechanics that you could compare their computation to. Because there isn't any known consistent way to modify quantum mechanics keeping cluster decomposition. Forget relativity, even without relativity.
Okay.
So I believe that's why Google didn't interpret their experiment as a test of quantum mechanics. It's somewhat similar to the reason that the LIGO people tend to not describe their observations as tests of general relativity. They agree with general relativity, but there isn't a convincing, well, it's not clear what's the competing theory you'd want to compare to. So they can't, well, it's artificial. It tends to be artificial to try to put limits on parameters in competing theories. You can do something, but anyway, the LIGO people tend not to do it. I think for the same reason the Google people didn't. Anyway, I think that's the trouble with your question.
Okay.
First, you have to decide how you want to modify quantum mechanics.
No, I agree. The idea would be to modify it, keeping cluster decomposition. If you say that's impossible, then
I don't want to say it's impossible. I'm just going to say that the literature doesn't contain a sensible suggestion, I don't believe.
Okay, okay.
I could be wrong. I definitely don't know everything in the literature.
Is it known which, like, if you take, for instance, quantum mechanics as from Dirac's little book, basically, right? The axioms, if you want, in there, like what there ties most closely to, I mean, like from which is part of this axioms cluster decomposition actually kind of follows, or which is it most closely tied to? So that you would know if you don't want to give a cluster decomposition, you are not allowed to modify.
Abstract. Well, Weinberg explored some modifications of quantum mechanics, which I didn't review for this lecture, and I better not try to talk about them now. But Joe Polchinski, and I don't remember exactly how this was related to Weinberg's work, but Joe Polchinski showed that in some modifications of quantum mechanics, you could signal superluminally at a distance. So famously, the Einstein-Podolsky-Rosen correlations cannot be used for superluminal signaling. But if you modify quantum mechanics, you're in danger of being able to signal superluminally. The reason I've told you this in answering you is that in Dirac's book, it's, I believe, sufficiently abstract that you wouldn't be able to talk about whether there's superluminal signaling. So you need to input locality or cluster decomposition along with quantum mechanics before you can ask whether the correlations can be used to make signaling at a distance. If you just say abstractly there's Hilbert space and operators, then you can't try, you need more than that to be able to talk about signaling at a distance.
Okay, thank you.
Sure.
Okay, so I think it's time to move to the last talk, and then we will have some time after for a general discussion. So the next speaker is Professor Nima Arkani-Hamed from the Institute for Advanced Study. Nima.
Can you guys all hear me okay?
Yes, yes.